Thank you. Thank you for having me. I will try to stick to time, given that coffee break is right after, even though I'm starting a bit late. But it's going to be a big change in topic and context here, because first of all, I'm not a social scientist. I'm a computational scientist and an engineer, and I'm going to focus on computational reproducibility in the understanding that the following speaker will focus in replicability, and I will explain what I mean by those two terms to start with. So this session on reproducibility and replicability, and my talk focusing on first the National Academy's report that just appeared in May 2009, this year, on replicability and reproducibility, and the practice of reproducible research is what I will focus on. A little bit about me, and as it regards to this topic, I published something that was sort of like a public pledge on reproducibility in 2012, which I called the Reproducibility PI, as in Principal Investigator Manifesto. I'll show you what that is. I published a sort of like a thought piece on anecdotes of my history on reproducibility in science in 2016 that I want to share with you. Our signature open science practice, which I call reproducibility packages, I'll explain what that is, was the topic of an interview in Nature blogs. I'm also the editor for reproducible research in computing and science and engineering, an IEEE publication. For this year, I'm a reproducibility chair of a very large conference, the Supercomputing Conference for high performance computing, one of the major conferences in computer science. And I was part of this study committee for the National Academies that I will tell you about. These are the pledges in the Reproducibility PI manifesto I made. The first one was that I will teach my graduate students about reproducibility. And so we have very intense conversations in my group all the time about what it is to do reproducible research. And it is part of what I consider my job as a trainer of my students. All of our research code, the software that we write, and the writing, the actual papers, are always under version control. I know that you've had some workshops on Git, and that's what we mean. We always carry out validation and verification. That will not have a meaning to you because this is a computational science context. It means proving that the simulation is actually solving the mathematical equations that you say or think it does, and it actually matches experiments. And for main results, we share the data. So main results, what I mean by main results is you publish a paper, there's a figure there, there's a table with numbers. A lot of figures in the area of computational science or computational physics. So for a result, a figure will be also accompanied by the data that is behind that figure. So for every dot, there should be a number that you share with your readers, the plotting script, so how you turn those numbers into a picture, and the actual figure. And we put that together into a bundle, put that on a sharing site under a CC BY license, and that's what we call a repro pack or a reproducibility package. That's secondary data that actually turns into a figure in your paper. We always upload our preprints, the manuscripts, to a preprint server at the time of submission to a journal, and we choose the journals that we publish in on the basis of what policy they have for preprint. So if a journal, regardless how prestigious it is, does not allow preprinting, then we just don't submit there. We made that pledge at that point, and we've been consistent with that. We release any research software that we created to produce a publication at the time of submission of a paper to a journal. That was the pledge that we made in 2012, that I made in 2012. But right now, we just develop in the open. So the code is being written, and it's being written in public from the moment we start working on it. We always add a reproducibility statement in the paper saying, well, this paper was done under these conditions of reproducibility, and here's where we shared the different objects that accompany this paper. And also develop a consistent open science policy and keeping an up-to-date web presence, because what good is it to say that you're putting all of your research objects in somewhere, sharing, if people cannot find them? So it's important to actually be proactive to communicating where you're sharing all of your materials. This is the hard road to reproducibility, a little story that I narrated in a back page of Science, where I was telling about how I struggled as a doctoral student when I was working with code that was left over by another graduate student who had already graduated and gone, had received no training in programming, and probably that other student didn't either, but he was a better programmer than me. I'm still a second-rate programmer anyway. My students are much better than me. But the story was that, I had to read this code and try to figure out what it was doing, and some of the variable names were in another language. It was horrible. I hated it. And so from that moment on, this is what sort of launched me into this concern about software and in our practice as scientists, and actually being a little bit more of more friendly with it, right? This little blog tells about this, in particular, this signature open science practice that we have, the reproducibility packages, and what types of tools we use to do that. And I will share with you all the tools that we use. And as I said, Computing in Science and Engineering is a IEEE publication that now has a reproducible research track, which means that the magazine is publishing articles about reproducible research and also research articles that emphasize the reproducibility aspect of how they are really open. Let me tell you a little bit for a few minutes about the National Academy's study committee. It published its report in May of this year, and it was I was in the committee. It was mandated by Congress, so it's in the law that this study should have been commissioned to the National Science Foundation, by the National Science Foundation to the National Academies. And it was 18 months of in-person meetings and teleconferences and then collaborative writing. So a lot of service work that was done by these 15 experts. And the report is available in the National Academy's Press for you to read. Of course, you can buy a paper copy, but you can also download the PDF for free or read it online. The first thing that the committee had to do was define reproducibility and replicability. You would think that's not so hard, but it turns out that across many fields, people have started to use these words in different ways. And sometimes they are in agreement, but oftentimes they're not. In particular, there are some groups that have chosen exactly opposite definitions for reproducibility and replicability. That doesn't help, because if we are going to agree on what it means to do reproducible research, at least we need to agree on what it means. So this was a very hard part of the task. And in fact, it was very frustrating because at every new meeting, it appeared that if we had made a decision in the previous meeting, we were back to square one arguing about the definitions. It was terrible. But finally, there are some definitions that were adopted and proposed in this report. And reproducibility is defined there as obtaining consistent results using the same input data, computational steps, methods, and code, the actual software, and the conditions of analysis. So in essence, it's a synonym with computational reproducibility. Can other researchers use the same data, the same software to get the same results? It sounds like it should be straightforward to do that. Same input, same software should give you the same answer. It turns out that it's not so easy. Much of it has to do with the tools that we use, and a lot of the computational fields, with big data and highly computational fields, it gets really difficult. A lot of tools are being developed for this to facilitate it, but you should be aware that it is a concern. It's not straightforward. But it has to do with transparency. One of the requisites, of course, is transparency. Replicability is obtaining consistent results across studies that are aimed at answering the same scientific question, but each one has collect its own data. So this is what you experience in most empirical studies. Of course, you're talking about replication, collecting new data to confirm that the findings are the same. A full replication study sometimes is impossible to do. For example, an opportunistic epidemiological study, you can't, or measuring things on when an earthquake occurs, you don't have another earthquake to measure, to take those measurements. But in contrast, reproducible research is just limited by the time and effort that we're willing to invest in the practice of computational research. These definitions are consistent with how they were introduced in the idea of reproducibility spectrum in this paper, where a full replication study involves collecting new data, perhaps with different methods, perhaps with the same method, but it's new data. And reproducibility is at the left side of the spectrum, where we're talking about we're sharing openly all of the materials and code and data that are involved in this study. A critical barrier to reproducibility today is the fact that most people don't publish the computer code that was used to generate the results, or it might no longer be available if we're talking about an already published study. All right, so I will focus on reproducible research. That is what I'm a computational scientist, as I said, and this may be a little bit foreign to some of you. Many of you are empirical scientists, but at the end of the day, you will have a computational step where you analyze your data, and so I hope some of this will be useful. Now, if you think beyond your sphere as social scientists or economists in the room, there are many other fields that use computation in a big way. You may have seen the recent breakthrough in, getting an image of a black hole. It was all over Twitter. And these type of studies are just, computation is so integral to producing the results. It's very prominent, of course, in various physical science fields and mathematical sciences, all of these fields that involve modeling and simulation, but of course, many fields that involve now big data, like in the case of astronomy. While the abundance of the report of the National Academy realizes and shares that the computation, the high-performance computing in particular, and the abundance of data has really transformed many fields of science, but it hasn't changed the way that we communicate science. We still publish papers, and we think that papers are the main way to communicate the science that we did, but papers are not enough. Just as an idea of the importance of software in general in science, here is some results from a survey done in the UK in 2014 of some hundreds of researchers in research universities in the United Kingdom. Of those that responded, 92% use research software in their activities. 69% say that the research would not even be practical without it, without software. 56% develop their own software. They're writing their own software, but 21% of those have no training at all in software development. I think that probably is worse in reality. People are mostly self-taught in terms of producing research software. Reproducibility requires having the complete software environment and the full source code available for inspection, modification, and application, and the various parameter settings. It was already said in 1995 in this paper of Donahoe and collaborators. Now, the complete software environment is more complicated than you might think, because you're using several other things that you don't know sometimes. Your operating system perhaps is doing some things, and maybe when you're using research software, even if it's an R script, sometimes the version of particular functions in that R script may change over the years. And so really keeping track of everything is more difficult than you might think. Here is a recommendation from the National Academy's report that I want to emphasize to you. It says that researchers really need to convey complete information about any computational methods and data products that support their published results. Complete information includes the software. And oftentimes that is not the case in the practice today. Sometimes it also includes details such as the operating system, the hardware that you use to run, any libraries, software libraries that people use, in addition to the software that they wrote themselves. Another recommendation is to explore the limits of computational reproducibility, because we really don't know in some areas, say climate modeling, for example. A climate model is run in very big supercomputers that have hundreds or thousands of processors communicating and working together to produce the result. And it turns out that when you're working in parallel computers, the order in which minute operations, arithmetic operations are performed sometimes changes the answer. So when you do climate modeling, in addition to having a very complex, system of equations, you have parallel computing. And then what is the meaning of having a consistent result? Is something that we need to agree upon and study, because it needs to be understood perhaps in a statistical, in an ensemble, and not just getting the exact same numeric answer. So it requires a little bit of the thinking. This idea of bitwise reproducibility means you get exactly the same answer up to all the digits of that number, and that sometimes needs to be relaxed in the context of parallel computing, for example. So what makes reproducibility so difficult to achieve? A number of factors can contribute to the lack of reproducibility. They are identified in the report. And in addition to lack of access to the non-public objects of research like data and code, there are other contributors. For example, inadequate record keeping. The original researchers may not properly record all of the relevant digital artifacts that were used in the research. Sometimes we don't realize that changing versions of some software will affect the results, and ideally these things need to be all documented. Of course, that's tedious, but that's where tools can come in to automate those things so that the researcher doesn't have to do everything in a manual way. Non-transparent reporting. The original researchers may not publish or give access to all of the relevant digital artifacts, the original raw data, materials, as it was mentioned before, but also the software secondary data and any analysis scripts and so on. Now, there's some more problematic issues like obsolescence of digital artifacts. Even if you publish your data, will that data be in a format that can be read in 10 years or 20 years? How many years do we need to plan for in the formats of the data, pieces of data that we share? That's a question for the archivists and the librarians and so on. Software, more complicated. If I write on my software and I publish it, will that software run in 5 years or 10 years? What is the computers change all the time, and so do the other pieces of software that need to interface and so on. Of course, there are possible flawed attempts to reproduce others' results as computational analysis becomes more complex, and the original researchers had to do a very specialized work to produce their results. Then obviously that same level of expertise needs to be present in anyone attempting to reproduce those results, and that is a lot of training that's required. And then the very difficult one is the barriers in the culture of research and the lack of resources and incentives to adopt computational, reproducible, and transparent research methods, because if we are still valuing careers just based on publications, on papers, scientific papers, then going through all this extra effort of producing transparent software and data and putting those in different repositories is kind of unrewarded. So how to improve reproducibility related to these barriers that I mentioned before? The first one is automatic capture of computational details. Doing this by hand is just too difficult in many areas of highly data based and computational science. We need workflow management systems. Imagine that example I showed you of the group that was able to generate an image of the black hole. The many sensors and instruments that were used, the many different pieces of software to produce the final image is multi-layers of technologies that need to be orchestrated, and that's what a workflow management system does. It orchestrates all of these pieces and keeps complete provenance of how a large data file has been altered or touched by any other piece of software or instrument. Source code and data version control. You've been talking about source Git. I saw in the agenda. That's version control for software. There's also data version control. Large data files cannot actually, you don't do version control in the same way because you're not going to be storing all the different versions of a data set, but you do want to have very complete metadata and do version control on the metadata of large data files, for example. So that's something to learn about in terms of new technologies that are coming in to help. Tools for reproducing results via virtualization, cloud computing, packaging, containers. These are new technologies that are coming into play as well, where you can package not just the software, but the complete computational environment that you use to produce some result, and share that in a way that the computer that the person is using does not interfere. It's like that's called containers, so you can actually run the software in an environment that is separated from the other pieces of software that you have in a given computer. Very valuable for computational reproducibility. And interactive computational notebooks. I love Jupyter. I'm a big fan of Jupyter. I'll tell you a little bit more about Jupyter in a moment. So one of the important recommendations, I think, of the National Academy's study is to invest in the development of open source and usable tools and infrastructure that support reproducibility. And I emphasize open source. I do believe they have to be open source. There are many recent technological advances that one becomes more aware of if you're doing more intense computing, like I mentioned, containers, for example. It's important that these be not only developed by the commercial players, but in collaboration with the agencies and the researchers, hopefully in an open source model. But the idea is that we want to make the creation of reproducible experiments, computational experiments, more easier and an integral part of scientists' practice, so that it is computational reproducibility becomes straightforward over time. I will tell you about steps that I believe are basic steps in computational reproducibility. Publish the software. It is something that I've believed for a very long time. As a computational scientist and engineers, we don't really have a proper discipline until we value software. That means software needs to be valued as scientific output of research, not just a paper. Sometimes creating software for answering certain research questions takes 2 years, 3 years, 5 years. It's very hard work, so it needs to be valued. Many savvy open scholars are working to slash the hurdles for researchers to receive academic credit for their output, including research software. So I want to tell you about one effort. The Journal of Open Source Software is a place where you can actually submit the research software that was created to answer some research questions and obtain a paper that is actually based on the software. You really just write a short description of the software, but the peer review occurs in the software. The reviewers download and install the software and run the test and check that the software was written to a given standard of quality, and they give input and advice on how to improve the software. The goal is to get a paper so that the author of the research software can get some credit out of that work, but also to improve the quality of the software. So I really recommend, if you write software for your research, to have a look at that opportunity. The JAWS is called. It is an affiliate of the open source initiative and also a fiscally sponsored project of NumFocus. NumFocus is a 501c3 charity that also provides fiscal sponsorship for your favorite Python open source projects like SciPy and NumPy and Jupyter as well, and many others. Pandas, perhaps you've used Pandas. In data analysis, it is a fiscally sponsored project of NumFocus. Because these little open source projects, they're not incorporated themselves. They can't receive money. They don't have. They're not corporations. So NumFocus provides that structure and many services. The JOS infrastructure, the journal itself is open source, so it was created with a publication management system that is also open source, so somebody can do another journal with the same system. And it uses existing infrastructure like the Zenodo data repository from CERN. I'll tell you a little bit more about that in a moment. The ORCID for data identification, Crossref for minting a DOI, a digital object identifier for your paper so that it can collect citations and can be cited and all of that. And a custom web app for submissions and management of the software that is also open source. So we are walking the walk and talking the talk. I'm in the board of editors of this journal. And I want to spend a little bit of time to tell you about open source because it's very important, and there are a lot of misconceptions about open source in general. And the reproducible research is vitally connected with open source software as well as open science. And I think it's important for every researcher that writes some code to know a few basic things about this. It can get very legal, very complicated, very fast, but there are a few basic things that we all should know if you are writing code. First thing to be aware, if you're a user of other code that people have published, that any piece of code that you find on GitHub, just because it's public and it's on GitHub doesn't mean that it's open source. It must have a license attached to it. So the original authors must explicitly attach a public license and say, these are the permissions I give you, dear reader, for using my code. If it doesn't have anything, what I recommend is you write to the author and say, hey, I'm interested in using your code. It's public on GitHub, but you forgot to put a license on it. Do you really want to put a license on it? Because otherwise I can't touch it. I can't use it. You haven't given me permission to use it. Software is automatically copyrighted the moment that is written, just like a poem. So you need a license to use it. Standard public licenses, you need to know a little bit about this. So it's not sufficient to make if you write software, it's not sufficient to make it public and just put it on a website. You must attach a license that allows others to modify and distribute the code, especially if you're expecting them to reproduce your results or if you're expecting that to go along with a paper. And so it's very important to know about this. If you find software on GitHub that doesn't have a license, you must assume that it's all rights reserved. If you put some software on GitHub and you want other people to use it, put a license on it. What license? Well, you should use an open source license that is public and already understood by the whole community. These are the licenses approved by the OSI Open Source Initiative. And a little bit about this. This paper I recommend very much. It's a short paper and a very good read about what every scientist that writes code should know. And the basic dichotomy that you need to be aware of as a researcher that writes software is this idea of permissive versus copyleft. There's a lot of misconceptions about this. And so these terms are often confused, and I will tell you what the difference are. Permissive licenses means that they have fewer restrictions. Essentially, you put the code out there and you say anybody who gets this code can use it, redistribute, modify. The only condition is that you give me credit as the author. So if you redistribute, it has to have my name on it as the author. That's all. So that's really the best choice, in my opinion, for academic use and the opinion of many people who write software. Two examples are the Berkeley Software Distribution, or BSD license, and the MIT license. Apache license is another choice. So if you see software with any of these three, it means you can do anything with it as long as you give credit to the author. A restrictive license is a copyleft license. Some people think this is more free because this guarantees that the software has, there will be perpetual access to the source code because it requires that any derivative works be under the same license. So they're also called viral because if you pick a piece of software that has this license and you write a derivative work, it has to be under the same license. People who really believe and some of the principles of open source say this is better because the software will always be open, but it gives you a restriction. It's not actually free as the other one, because if you want to create a commercial product and build some piece of software where bits of it are actually your product and proprietary and use some open source software, the open source software that has a restrictive license is not going to allow you to do that. So for academic use, I always say that simple and permissive is best. BSD3 for code is what we use, the Berkeley Software Science, and CC BY Creative Commons with attribution for any other content, any written material, any figures that you want to share. CC BY, those are the best options in my opinion. Step 2. Step 1 was publish your code. Step 2, reproducible workflows. You've already been learning about version control, but there's more to that. Version control, of course, provides a lot of automatic documentation of all the changes that have happened on any software you're writing. But the second point there, scripting, automating, and documenting is very important as well. Automation is essential when it comes to data analysis. And what do we mean by automation? Automation is turning protocols into code. That's in a nutshell, turning protocols into code. You want to script out any sequence of steps that you're taking to analyze your data, because if you're doing them interactively, you will forget what you did and there is no record of what you did to that data. So automation is essential when it comes to data analysis. Having the analysis in a script and not produced by typing and clicking, this is really, really important for reproducibility. And it is the reason why we insist in some command line skills that you actually be able to operate by typing commands in a text instead of GUIs. And automating parts of your whole workflow is very important of a skill to learn. Avoid GUIs like the plague, even for manipulating figures. And I'll tell you more about what I think about Excel in a moment. An essential technology for collaborative code development is, of course, version control, this system to automatically record and manage every changing version of any source code that you're writing. It preserves a complete history of any changes to a text file and also who did it. So it's a very important command there is git blame. Who did a change that broke the code is very important to know. Who made the changes, when, and also the opportunity to roll back to a previous version is very powerful. So is something that is hard to learn, but is totally worth the effort if you are doing any software, developing any software, especially collaboratively. So use version control. We use it all the time. We not only use it for code, but we also use it for writing, for our own internal reports that we write on Markdown or Jupyter notebooks, and even the manuscripts that we write on LaTeX. We're doing that on GitHub. We're now writing our papers on GitHub in public, under version control. The whole history of the paper is there. Who wrote what is also available in the history of our manuscripts. GitHub is more than just a place to post your code and materials. It really is important to understand that beyond hosting files, it helps you coordinate as a team, and these things improve the quality of the computational work that you do. The interactions between not only your team, but you and your potential readers can be streamlined using the collaboration tools of GitHub. The idea, for example, that code can be forked, as we say, and then changed, and then your changes can be supplied back to the original author via the coordination that's called the pull request. These things are really tools of coordination that can improve the workflow, and it is just brilliantly structures the way that we can interact with our teammates and potential future collaborators. But beyond version control and using GitHub for collaboration, there's an important idea that I want to emphasize, which is open source as a development model. Linus Torvalds, who is the author of the Linux operating system, said it best, given enough eyeballs, all bugs are shallow. So if you develop in the open, which means you're writing your software, and as the software is being developed over time, it is public and your collaborators can see it, and anyone who is participating in the team can see it. If there are bugs in the code, there's better chance that they will be found before you publish that paper and with a mistake. Jupyter. Jupyter is a fantastic project. I am really in love with Jupyter. It's a set of open source tools for interactive and exploratory computing. And many people think that it does help in our quest for reproducibility, because it allows you to use code and communication with just language in an integrated way. As part of the original grant proposal that the Jupyter project got a few years ago, they describe the core problem that they are trying to solve as collaborative creation of reproducible computational analysis. And some researchers object to characterizing Jupyter notebooks as good for reproducibility because they point out so-called problems with the ability to go back and edit bits of your computational workflow interactively and in a nonlinear fashion, and that can confuse some people. But I have found that most of that can be solved with some just good habits of restart and run all before you ship that Jupyter notebook, and understanding unordered execution and keeping tabs on this, just not doing messy work. But one thing that I want to point out is that this is an interactive tool, and sometimes there's some tensions between interactive and reproducible. So what makes Jupyter different than, say, the dreaded spreadsheet? And in some of the people who talk about reproducibility say that interactive problems are tyranny unless they include the ability to arrive at any previous state by means of a script. So interactive GUI-based programs are not conducive to reproducibility. So there's a difference here between Excel and Jupyter in how they implement interactivity. I'm sure many of you know here about the story of the economists Reinhard and Rogoff, who published a study in 2010 called Growth in a Time of Debt, suggesting a negative effect of growth from the national debt, and the fact that then a graduate student requested the data and found that there was an error in the spreadsheet that led to that result, and in fact it had a serious problem and various bad consequences, leading to many analysis of this and commentary about this shocking bug in the Excel sheet. Very sad situation, but in other fields also a lot of problems can occur from using a spreadsheet. In genetics, for example, it turns out that Excel can grab numbers such as a gene called with a code SEPT2, which is septin2, but SEPT also can be interpreted as September, and it's a date, and Excel turns it into a date and automatically, and then all your data is corrupted. It turns out that 1 out of 5 publications using Excel for gene lists contain errors, according to this study. So if you think that the issue can be fixed by formatting Excel columns of text and remaining vigilant, another solution is just not using spreadsheets to do data analysis. I have a friend that tells it like this: relying on Excel for important calculations is like driving drunk. No matter how carefully you do it, a wreck is likely. So don't do it. Don't do it. The problem with spreadsheets is that they conflate input, output, code, and presentation. So it makes testing code almost impossible and discovering bugs very, very difficult. So it's tempting, they're easy, but if you're doing any serious data analysis, you should not be using Excel or Google Sheets or any spreadsheet program. We need to design tools for reproducibility, tools that actually have reproducibility built in. We need to look back into concepts of human-computer interaction, the basics of design of interfaces. For example, a standard in designing the user interface tells us that tools that succeed are comprehensible, predictable, and controllable, but those who have authority and responsibility must have adequate levels of control. Responsibility should guide design. Who has responsibility for the study? We do, the humans, not the computer. So we need to take that responsibility seriously, and the tool needs to enable us to take that responsibility. Any tool that claims to provide reproducibility in one click is probably not a solution. There should be a combination of human control and automation. We need to remain in control. It's important to think about the design of our tools as when we are trying to enable reproducibility. And because I'm aware of the time, I will just skip ahead to this point. This is just explains how Jupyter works in this idea, because I believe Jupyter, for example, is the interactivity that it gives you is different from Excel because you remain in control. And the punchline here is that a push button solution does not exist. Reproducibility is essentially about trust. Trust is engendered by relationships, the relationships between you as scientists and as you as scientists with your tools of interaction in the process. And we can't just depend on tools to do it all for us. It's not a one-click solution. And the third step is open data and open science. Archiving all interim data is important. Sometimes we, in simulations, for example, use something called a mesh, which is a very complex geometrical object where we do all the computations. People don't share those objects. They're big files, but there's no problem today to share those files in an archival repository. Sharing all input files, configuration, parameter lists, and runtime options that you use. Sometimes these things are not even documented. And archiving any secondary data, this idea of the reproducibility packages that I was mentioning. Good data management is very important. You need to learn about what's called the FAIR principles and what it means to actually manage your data properly so that it's findable, accessible, interoperable, and reusable for both machines and people. Data repositories, you must use data repositories that provide a unique global identifier for your data, typically a DOI, and they must offer long-term preservation guarantees. So it's not enough to just place your CSV file on a GitHub repository. Even if it's a small piece of data, you need to put it in a repository that gives you a DOI for that, and it gives you permanent storage, and you can always cite it and find it. Remember, authors of a GitHub repository can always delete that repository. GitHub does not provide any guarantees of persistence. So even for your code, if you want to share your code, you need to put it on Zenodo or something that will give you persistence and a DOI for that. GitHub is not enough. Some data repositories that I want to emphasize: Figshare, Zenodo, as we use those a lot. Zenodo for large files, Figshare for presentations, and so on. Figshare is general purpose and free and unlimited for public items. Zenodo was created by CERN. They allow larger files, and they provide a persistence up to 10 years, or they say can it be even infinite. They save all of the data from the big physics experiments in CERN, and I think they figured that they have to store so much data that storing all of the other data of all other researchers was just like the long tail for them. So they decided to just provide the service for free. So it is trustable. I'll skip that part of open publishing and emphasize the importance of preprints, because sharing openly your work in a timely fashion is also important. Increasingly, more and more fields are accepting preprints. It used to be that biologists, for example, would never publish preprints, but nowadays they do. They have bioRxiv, and most journals accept manuscripts that were previously submitted to preprint service. So preprint, good idea. These repro packs, what we do, as I told you, for the main results in a paper, we share the data, the plotting script, and the figure under a CC BY license, and put that on Figshare, and we get a DOI for it. So when I publish a paper, the figure that has my results, and I've previously to publishing the paper, and at the moment of submission, we've put the file, the data file behind that figure, the Python script that generated the figure, and the figure themselves as a file bundle on Figshare. I get a CC BY, I put a CC BY license on it, and I cite that file bundle on the figure caption, with the added bonus that that figure now can be reused by any other researcher who wants to reuse it without asking permission to the journal, even though you transfer the copyright of the paper to them, because you're using the figure under the CC BY license that you've slapped on it before publishing it. So it's a good trick. I recommend it. That is our workflow. Write the paper, zip all the figure files, put them on Figshare, get a DOI, cite the DOI, and share it before you publish. To end, this is my last slide. These are the top challenges, I believe, in reproducible research. First, creation, curation, usage and publication of research software. You must publish the software, otherwise we don't know your methods. The scientific paper is not enough today to convey all of the information about how a result was achieved, especially if you're doing big data analysis or simulation or modeling based research. Second big challenge, acceptance, adoption, and standardization of open science practices. If we don't all do these practices, then some people are going to be disadvantaged because we're spending a lot more time to actually publish those papers with all of these standards of quality. But if journals are requiring it, if funding agencies are requiring it, and we're all agreeing that those are the basic standards, then it raises the bar for everybody, and that's good. Misalignment, this is the hardest one. Misalignment of with academic incentive structures and institutional processes for career progression. I don't know the answer to that. In my talk, I've shared all the things that we've learned about the first two, but I don't know anything about what we can do about the third. Is the hardest challenge, I think. Maybe it is something that the social scientists can come up with an idea on how to address this. Thank you very much for having me.
I think we have some time for some questions.
And that was 44 minutes. I stuck to time. I always tell my students, the best thing you can do for your audience is stick to time.
Hi. So I'm particularly interested in the aspect you touched on sharing a software environment, and you mentioned containers and automation of registries. I wanted to ask you if you could elaborate on that, or if you advocate for any particular alternative between those two, or what are the current best practices that are on that?
Right. In industry, I think Docker containers have become a standard. Docker is a technology for what is called containerization or virtualization, where you can package the whole computational environment. So you would have, essentially all of the layers of software that are required to run some software-based analysis, or you can even contain the data itself in the whole container. There's a few ingredients there. One starts by writing what's called a Docker file. The file is just a text file, and human readable file that lists every single piece of software that you're using and the version and the commands on how to install it. You can also use that with the Docker software to create a whole image of your environment, and then you can share that image in what's called, it's a registry, Docker Hub. So you can upload that to Docker Hub and then provide a link, so anybody else that wants to use that image, they can just download it. That saves a lot of effort because they don't have to install all the pieces of software one by one. We just have a paper that was accepted. I haven't put it on my website yet, but the archive preprint, of course, is out, on using Docker containers combined with cloud resources. So instead of people running on their machines, you're running on Microsoft Azure or another cloud provider, commercial cloud, and then if you provide a Docker image of your whole software environment, you can and it's running in the cloud, another researcher could essentially copy over that image to their own cloud account. And in addition to having all the software, you provide all of the configuration files so that they can generate the exact same hardware configuration on the cloud, the same type of nodes, the same type of everything that the virtual machine that you create on the cloud is also stipulated in a recipe, and so then it's like really reproducible. But in addition to that, many new products are being developed to facilitate these things, that if you don't want to actually do that all by hand and have to learn how to use Docker, because it really is a little bit specialized, you could use other tools that provide a full platform that actually does all of that behind the scenes for you. So all the Docker, creating the container, creating the image, it's done behind the scenes. You'll learn more about that today, I think. There's several providers of cloud solutions with containers, and you just create an account and you do everything on the cloud. So, but very interesting technology solutions are coming up to facilitate these things. We just need to disseminate them, start using them, then start requiring them for our workflows.
Sorry. Again, another very interesting talk. One specific thing that stuck in my mind is this idea of obsolescence and how, and basically, I could see that one argument of the users of proprietary software will say, "Hey, I'm going to use data because for the next 10 years, I think these guys are going to be in town and they're going to guarantee me that my software is going to run all the way back." Not sure if that's true, but do you have any experience or thoughts about like the rates of obsolescence of proprietary versus open source software?
I don't, but proprietary, in my opinion, it's just not a tool I consider. If you're using proprietary software, I don't consider that reproducible because I need to see exactly what the software is doing. It needs to be inspectable by others. A proprietary tool doesn't give me the level of transparency that I think is necessary. In terms of your real question, which is, does open source and proprietary differ in terms of what they can guarantee over time? My gut feeling is that open source is going to be better because you can always, go back and see exactly what is different from version 10 years ago and the version today and why it's not working. You cannot do that with proprietary tools. Now, I think the conversation about obsolescence of digital artifacts has to be with the archivists also in the room and the library people in the room, and we need to come up with an agreement of how long is it reasonable to ask for the research objects to be operational. Sometimes, we don't need things to be operational for 20 years because the science is progressing at such a pace that in 20 years this result is really irrelevant. So it depends on the scientific field how much of a time requirement we're going to give. But I think in terms of data, it's extremely important to come to agreement on standard formats that will be robust. I think standards is the way to go.
Just to follow up quickly on that, as somebody who works in a gigantic data repository, what hardware standards do we need to store data? Beyond just the manner in which it's readable by software. So we only just recently at the Census Bureau got rid of the computer that was purchased in the 1950s and read off of tapes. And so when I think back to some of the data that we still hold, we don't even have tape readers anymore that we can take the data off of the old tape files. So it's something that has crossed my mind that is also an issue that we need to worry about is the changing nature of data. What happens when we have quantum computers and,
Yes, I have no clue, but it is a problem we need to keep in the conversation.
I think that's going to be our last question, then we'll go to a break.
Yes, thank you.
So this is actually more trying to provide support than a question, but I just wanted to point out two things. One is Gregory Kurtzer's job was supporting all kinds of old crusty software, and he developed Singularity, and he was able to negotiate with all the researchers and say well, okay, I promise you I can support, Red Hat and Scientific Linux of these versions. Is that going to be enough? Can we upgrade the cluster? Right? And there was this path forward, and that was in large part because he had the ability to architect these open solutions and the tools inside were open enough. And that sort of bridges into the other piece, which is you can't archive Stata so that other scientists can go get the version of Stata you use. That is against the law, right? You can totally archive whatever version of Python or R you used, and in fact, there's already people doing that for you. So I mean, there are. I think you can speak a little more certainly about that issue. And certainly I welcome arguments to the contrary.
Agreements about what is reasonable still need to be made, right? Requiring a software to run in 20 years might not make sense for some fields, but might make sense for other fields. Yeah. Thank you so much for your attention. I know some of this topic might be outside of some of your areas of concern, but I hope that I piqued your curiosity about the role of software in research. Thank you.
Thank you.